talk about an alternative for the Rydberg quantum processors, which is empowered by the Fermi scattering of Rydberg electron from the plaquette atoms. The Rydberg Fermi scattering has been widely studied in terms of Rydberg molecules, and it has been observed in the spectroscopy of the BEC. The interaction contains S and P wave scattering terms, and the interaction I plotted it here, where the oscillations are generated due to the presence or absence of the electron. To deploy the Rydberg Fermi scattering for quantum information, I need to have a qubit-dependent interaction, and this could be obtained by localizing atoms, but by using a spin-dependent lattice and localizing atoms on the nodes and antinodes of the Rydberg wave function, depending on their spin state. To further enhance the interaction, I need to concentrate the electron cloud close to the position of the plaquette atoms. And I found that if I generate a specific Rydberg superposition state, I would have constructive and destructive interferences at the position of the plaquettes and elsewhere, further concentrating the wave function at the position of the plaquettes. And this could be obtained by using linearly polarized lights propagating along Z direction. I just write them in terms of right and left circularly polarized light, and by tuning the two angles, I can have destructive interference for the MJ 1/2 and end up with the desired wave function that I like. And to quantify the interaction-induced level shift, I use the mean Rydberg Fermi interaction averaged over the Vannier state, a qubit-dependent Vannier state. And I also find the mean deviation that gives me the line broadening, the interaction-induced line broadening. For N64, I find 2.5 megahertz interaction at each qubit state, at each plaquette site, with a line broadening of 250 kilohertz. Another alternative for spin-dependent lattice shift is perpendicular to the lattice plane. This would suppress the line broadening. And you can see some examples for N74 in this slide. Now I want to use this for quantum computation. I just give an example for TOEFL EC4 not here. I have control atoms sitting on the plaquette, and the central target atoms that is getting excited to the Rydberg level. If all the control atoms are in one control state, there would be no atom in the wave function of the Rydberg central atom, and then the laser would be in resonance, and we excite and get a pi phase from this 2-pi rotation. In all other cases, we have at least one atom in the wave function, and this scattering makes the central atom out of resonance and blocks the transition. I quantified the fidelity encountering spontaneous emission rotation and spontaneous emission and rotation errors. The important point is that is the contrast of the Rydberg population in this model comparing to the previous dipolar model. Here, out of 2 to the power of k plus 1 qubit configuration, only one of them contains one Rydberg atom population, while in the dipolar system for ck naught, we have the scale of Rydberg population is proportional to k. And this would make a significant impact, since the main bottleneck in the Rydberg simulators comes from the short lifetime of Rydberg levels. And I also look at the scaling. So the interaction to loss scales by n to the power of -3. So if we go to smaller n, it's advantageous. although the interatomic distances would be smaller, and that would raise the errors from the single site addressing and laser crosstalk. Other approaches in enhancing the interaction are obtained by working with some quantum numbers. For example, orbital angular momentum quantum number L. If we enhance it, it would enhance the centrifugal force, pushes the electron from the central core towards the placket atoms and enhance the interaction. For example, you can see figure B, you can compare figure B and C with D and G orbital angular numbers. And you can compare their interaction changing from 1.2 to 1.7 megahertz. Also, I should point to, I need to suppress the qubit-dependent lattice shift to enhance the Frank-Condon factor in the spin rotation. And this could be obtained by increasing the number of angular nodes in the wave function, which is given by J minus MJ quantum numbers. So here, for example, in D, we have two angular nodes, but in E, we have 4 angular nodes. And you can see that the required qubit-dependent shift changes from 100 to 45 nanometer. Another interesting point is using circular state with maximum orbital angular number. It has a donut shape wave function, pretty confining the wave function to the placket atoms, as you can see in BZX cross-section perpendicular to the lattice. And we can gain 39 megahertz interaction. The other approach is using cesium atoms. They feature strong resonance at relatively low kinetic energy of electron, which allows harvesting this strong P-wave scattering at the large interatomic distances. I found that at 180 for 64D, which is coupled by the hydrogen manifolds of 43, 42, and 2 other states, I can gain 365 megahertz, and this strong interaction has also been observed in the experiment by Professor Schaffer. I also discussed and quantified the errors associated with single site addressing. I introduced 2 approaches for shining a laser and applying a light shift, or by using the darkest state approach. And I conclude that with the mentioned range of interatomic distances, the good rotation fidelities in the order of 10 to the power of -3 is achievable for the gate operation. At the end, I discussed the advantages of this system. One of them is that we only use 1 continuous laser pulse, a 2-pi pulse, and this would close the previous decoherence models that are caused by unprotected Rydberg population from the laser. The other approach is that the other advantage is that we significantly reduce the Rydberg population. In C6-0, the Rydberg population is 1,000 times suppressed over the gate operation. Also, we significantly compress the processor, and this would address the current shortage of laser power for scaling the optical lattices. The new model operates at very small interatomic distances. It doesn't suffer from level mixing or and the type of interaction is a restoring force, which does not destroy the trapping at short interatomic distances over a long time. At the end, the last but not least, in dipolar scheme, if we want to apply the K0 in fast scheme, we excite all control atoms, and then there would be unwanted intra-component crosstalk that reduces the fidelity. But here we do not excite the control atoms; we only excite the target atoms to the Rydberg level, and there is no intra-component crosstalk here. And at the end, thanks for your attention.